Hi everyone. In this video we're going to continue on with chapter 2 where I would pick up where I left off last Friday and what we would do on Monday at least. Okay, and so we left off at these measures of position. So we talked about measures of center and measures of variability recently in class. Measures of center, mean, median, and mode. Measures of variability, standard deviation, variance, range, so on and so forth. And where we kind of left off was that we had an idea of what measure of center and what measure of center I should use if the data is symmetric and if the data is skewed. So last time on Friday, I went through and we made sure that, sorry, that's my washer and dryer finishing, if you hear a song in the background. So we talked about if the data is symmetric, we should use the mean for many reasons. And if the data is skewed, we should use the median because it is a resistance measure. It's resistant to outliers and more resistant than the mean to skewness. But we never found out what we should use for skewed data and a measure of variability. If the data was symmetric, we decided that we should use the standard deviation. But what if the data is skewed? The standard deviation is not a resistance measure. It is really affected by outliers. And so that's what we're going to have to define here, or that's what we're trying to find. And to do that, we need some new things. And this new thing is called a measure of position. Measure of position. And so one class got to this and the other class didn't. So for the class that did, I'm sorry. This is a little bit of a review, but maybe it's a little review is probably a good thing. So a measure of position doesn't care about the actual value of the data point. Like, I don't care that you are actually 65 inches tall. I only care where you fall within the rest of the data set. Are you in the middle? Are you the first? Are you the lowest? Second lowest? So on and so forth. And so that's where we get the idea of a percentile. And so a percentile is the value such that P percent of the observations fall below that point. Okay, so we often see percentiles, or I often encounter percentiles in standardized testing. If you took the SAT, they'll often give you a raw score and then a percentile that you scored in. So you might have gotten a 600 on the math portion of the SAT, and that translates into the 72nd percentile, meaning that you did better than 72% of the people who took that test. And so that is a percentile. It's the point, I'm sorry, it's the point such that P percent of the observations fall below it. Okay, and so that's a percentile in general. And then we have some special percentiles. And these special percentiles are called quartiles because they cut the data up into quarters. And so to cut something up into 4 equal parts, you need to make 3 slices, so to speak. And so we have 3 quartiles that cut the data into quarters. The first quartile, which we'll call Q1, is the 25th percentile. The second quartile, Q2, is the 50th percentile, or that also is special, and that's called the median. So the median is the 50th percentile, is Q2. They're all the same. And then Q3 is the 75th. So we cut the data at 25, 50, and 75, and that makes our quartiles. And we need these quartiles because it's how we define the thing that is going to be the answer to my original question. And the question was, what should I use for a measure of variability if my data is skewed? Or what should I at least think about using? And the answer is the IQR, or interquartile range. And the interquartile range, if I describe it, it measures the variability in the middle 50% of the data. Middle 50%. And so it actually uses, and my apologies, actually I never fully define it here, and so let me define it. This is my bad. Okay, the interquartile range measures the variability in the middle 50% of the data, and it's found by subtracting Q1 from Q3. So Q3 minus Q1 is the IQR, hence the middle 50% of the data. So 75th minus 25th percentile. 50 percentiles are in the middle. And it is a resistance I'm sorry, excuse me. It's a resistance measure for the same reason that the median is a resistance measure, because the median, like I was describing before for measures of position, doesn't care about the actual data point. It's only where it lies in relation to other points. And so it's not affected by a really large or really small value or a few really large values, so on and so forth. And so if the data is symmetric, you should use the mean and standard deviation as measures of center and variability. If the data is skewed, you should use the median and IQR. And so I guarantee that I'll ask that question on some form of assessment, okay? Either the first exam or the final. Somewhere it will happen. And so make sure that you star that, write that down, remember that. Now, the IQR is just a number, and it tells us about variability. Like other measures of variability, it has to be positive unless all of the data points are the same. So the IQR is going to be positive, and the larger the IQR, the more variability that exists in the data, like the other ones. Okay? But the IQR can also be used for something else, and that something else is detecting outliers. So we defined an outlier as a point that falls away from the rest of the data. It doesn't look like the rest of the data in some way. And some outliers are obvious, and we could all see them and detect them just by looking at the data right away. So if my data points were 10, 15, 20, 25, and then 15,000, everyone, I think, would be able to say that 15,000 is an outlier, but some outliers are not as easy to detect. And so a way, I'm not saying it's the best way or the only way, but it is a way to detect outliers, is to use the IQR. Specifically, an observation is a potential outlier if it lies more than 1.5 times the IQR above Q3 or 1.5 times the IQR below 0.1. So I do Q3 plus that 1.5 times the IQR, and whatever that cutoff is, if a data point lies above that cutoff, it's a potential outlier. Similarly, Q1 minus 1.5 times the IQR, that's the low cutoff. And if a data point lies lower than that, it is also a potential outlier. I'm not saying it is an outlier, it's just a potential one. Okay, so let's take a look at StatCrunch and do some more summary. So if you weren't there on Friday, this will be a chance for you to look at StatCrunch a little bit more. If you were there on Friday, then you'll see it more. So this is my group. So when you get a StatCrunch license, so when you pay the money to get StatCrunch, I have a link in the syllabus that tells you to join my group. And so here's my group. It's called 117 Math 117B Fall 2023. It currently has 25 members. Okay, and so a lot of people have not joined this because there should be 70 some members in here, which is fine. But you will need to join it eventually. Okay, and when you join this group, you'll see now if you look, some data sets. So I've uploaded 4 data sets to start with up here. And they are large data sets that we can do various things for. And so let's start by looking at the Star Wars data set. Okay, so the Star Wars data set has a bunch of things in here: names of the character, the height, the mass, the hair color, the skin color, eye color, birth year, gender, home world, and species. And so we're looking at quantitative stuff, so it might be interesting to look at the mass of these various, how much they weigh, okay? And there are some NAs in here and some other things, but we aren't going to worry about them right now, okay? If we wanted to find the summary of a specific column, okay, for instance, mass, we would go to stat, summary stats, columns, okay? And it's going to ask which of the columns you want to summarize. And notice that StatCrunch is smart, and it doesn't give you all of the columns because all of the columns aren't quantitative. So it only gives you the ones that it detects are quantitative, which are height, mass, and birth year. So I want to do mass, okay? And then I'm going to come down here and by default, StatCrunch calculates a number of statistics, which you can see over here. Okay, but it's got even more. And so something that it doesn't have over here that I want, because we just talked about it, is the IQR. Okay, and actually, so it took away something. So maybe I want the mean. And it will tell you down here if you hover over it. Mine, because I have a Mac, is going to be different than yours. But for me, it's Command click. For you, it might be Control click. So if I want the mean, the standard deviation, I'm holding the Command key on mine, but the Control key probably on yours. Okay. And Q1, Q3, and then IQR. Now, I could have, it originally gave me Q1 and Q3, and I could have calculated the IQR, but I want it to show it to me anyway. Okay. Let's see, it also gives the median. And let's see. Okay, so there it computes and it gives me all the summary statistics I want. Okay, Q3 was 85, Q1 55, IQR 30. Okay, mean 97 and standard deviation 169. Okay, so if we were to look at these summaries, and I would ask you, does it seem like this data is symmetric or skewed based on these summaries? You might be able to tell me something. So the IQR and the standard, so the mean and the median are a pretty direct comparison. If they're very similar, then it's going to be probably pretty symmetric. So if the mean and the median are similar or the same, there's a good chance that the data will be symmetric. Right? The IQR and the standard deviation are less of an apples-to-apples comparison. But they are interesting. It is interesting that the IQR is very much smaller than the standard deviation, which leads me to think there might be something interesting going on here. So why don't I make a graph? Something else that we haven't done. Okay, and so I could go to graph, and we've talked about a histogram. And so here's a histogram. I can click histogram, mass, and click compute. Okay, and so if I look at this histogram and our discussions in class, you were there for our discussion of histograms in class, excuse me, you might be wondering, or you might be thinking that this just has too few bars. Which it does. It has 2 bars, almost all of the characters, so a frequency, 58 of them are between 0 and 200, and then 1 of them is between 1200 and 1400. And so that's interesting because, well, why are there only 2 bars? It should probably make more of them. And I guess the answer is that it's trying to include this bar down here. It's trying to include, there is one character in Star Wars that is very large, and they're trying to include that with everyone else, but it doesn't give us a really nice picture. And so there might be a few ways. So down here, if we look far enough through these options, there might be a way for us. So bins, start at, and width. And so we can, well, there's a few different types here, but we could, if we wanted to, I'm not going to at the moment, add where we want our bins to start at and the width of the bin to get a better picture. Now, if you know Star Wars, you know that the thing, person, place, or thing that is very big is Jabba the Hutt. If you've watched Star Wars, if not, that's fine. There is one character. Sorry, this does not scroll very nicely. If you look through the data, there aren't that many. Some of them don't have a mass, but there is one eventually. There, Jabba, last name I won't attempt to pronounce, whose mass is 1,358. So if I would change this data set, and for purposes of showing you this, I am, but I would tell you never to change a data set, never change the values in the data set, okay, just to make it NA and give you a similar picture. Okay. Now we see something very different. Now we see something very different with the histogram. It is not the picture of symmetricity. It isn't perfect symmetricness. Okay. Maybe slightly skewed to the right, but not really. So I would say this is fairly symmetric. Okay. And if we did a similar calculation than we did before, it's going to have the same roughly stuff in here. The mean is now 75. It was 97. Median 79. These are pretty close, and so hence more symmetric. Okay. Variance, or rather standard deviation, which was 100 something, okay, is now roughly 30, which actually, if you calculate Q3 minus Q1, is 29. And so they're very close, which makes sense in a symmetric kind of graph. Okay, although it isn't always the case that standard deviation and IQR will be similar in scale. Okay, so that's enough. That's enough for StatCrunch at the moment. And so I'm going to continue on a little bit. And so here's a quick demonstration that I have a few data points, okay, to show you that standard deviation is not a resistance measure, whereas IQR tends to be more of one. For data that is roughly symmetric, or they're all at least similar, standard deviation, IQR in the top one are the same, and the bottom one very much not the same. Where I changed one number from 18 to 1800, big effect on standard deviation, almost no effect on IQR. Okay, now, the next and probably second most popular type of visualization beyond a histogram for quantitative data is called a box plot. And a box plot uses the measures of position that we just talked about before to make a graph. And so here's a box plot. Okay? A box plot is made up of a box and what are sometimes called whiskers. So you might know this as a box and whisker plot. But the box part is made up of 3 lines. So there's a box and there's a line in the middle of the box. The leftmost line is Q1, the middlemost line is Q2, and the rightmost line is Q3. And so a box plot is nice as a question that I might ask you. I could give you a box plot and ask you to calculate such things as the IQR, because it's fairly easy to look at a plot and calculate Q3 minus Q1. Okay, so that's the box. The next part are the whiskers. Okay. And so the whiskers are made up of this calculation that I was talking about before to assess if there are outliers or not. And so the whiskers are formed by doing this calculation. So Q3 plus 1.5 times the IQR and Q1 minus 1.5 times the IQR. Okay, and so you get the 2 whiskers. Now notice in this graph that the whiskers aren't the same length And if I use those calculations that I have up there, they should be the same length. And so that might cause confusion. Well, it's actually the minimum or that point, and then the maximum or the other cutoff. So the minimum or the cutoff, and then maximum the cutoff. So, and then any points that fall beyond the whiskers are potential outliers. And so that is a box plot. Okay. Now, what we're going to end on for this video is something very special and another method of how we can gauge whether how surprising or extreme an observation is. And so one way is this box plot kind of idea and the Q3 plus 1.5 times the IQR. Okay, and the other one is called this. It's called a z-score. Okay, and so a z-score is formed by taking the observation from the data, subtracting it by the mean, and then dividing that result by the standard deviation. The formula looks like this. And so we know this formula for all of the things that we've done so far. So x bar, x with the bar on top of it, or x bar, is the mean. S is the standard deviation. X is just a data point. And then the result is z. Okay? And this has a nice interpretation. So this number has a nice interpretation. Its interpretation is that the observation x is z standard deviations away from the mean. Z standard deviations from the mean. And if we combine this knowledge with the empirical rule that we saw just a little bit before as a way to interpret S by itself, any point with a z-score of more than 3 or less than -3 should be considered a possible outlier. Of course, now the empirical rule is only valid for data that looks like a bell or a mound-shaped curve. Really, data that's symmetric, it's probably okay for. Okay, and so what I want you to do is take this little example. Okay, assume that the distribution of times that it takes students to complete a stats final is bell-shaped with a mean, so it matches that shape, so we can use the empirical rule, and thus we can use a z-score, with a mean of 68 minutes and a standard deviation of 10 minutes. And so with those pieces of information, I guess as a hint, that gives you x bar and s. Okay, I give you 4 different numbers, which you'll plug in for x, but use the formula that I had on the previous page to find the z-scores for each of the following exam lengths, and then answer the question, are any of the observations unusual? Okay, and that's where I'm going to end this video.